Okay, so I'm doing problem 43 from chapter 10. It says, a top has a moment of inertia equal to 4.0 times 10 to the negative 4 kilograms meters squared. So let's write that down. I equals 4.0 times 10 to the negative 4 kilograms meters squared. What else? It says a string wrapped around the peg along the axis of the top is pulled in such a way so as to maintain a constant tension of 5.57 newtons. So this string over here is pulling the top with a tension of 5.57 newtons. And then they say that after you pull the string 0.80 meters, how fast is the angular velocity of the top? So to begin, we'll first write what the sum of torque on the top is equal to, which is just I alpha. Replacing I alpha with its linear component, we get I A over R, since A is equal to alpha R. Next, we can change torque into force times the radius R, which it is being applied at, so that's I alpha R. Now, we can manipulate this expression and make it into A equals FR squared over I. Following that, we can set up our basic kinematic, which says V final squared equals V initial squared plus 2 acceleration times your displacement. Since we know that the top started from rest, this just goes to 0. And the delta x is just going to be 0.080 meters, right? Since it's being pulled 80 centimeters. So before we do anything with this, however, let's change our V final into its angular component. So that would be omega r squared times 2. Instead of alpha, we'll use the expression we got for acceleration up here, which is 2fr squared over I delta x. Expanding this whole term out, we get omega squared r squared equals 2fr squared over I times delta x. The r squareds on both sides cancel. So what we get is that omega is equal to the square root of 2f I delta x. If you plug all the values in, so we have a force of 5.57 newtons, a moment of inertia of 4 times 10 to the negative 4 newtons per meter, and a displacement of 0.8 meters, we get 2 times 5.57 times 0.8. If you plug everything in your calculator, you should get 149.26 and radians per second as your unit. And that's how you solve number 43.